Thank you, Dan, for that very kind introduction, and it's a privilege to be here this afternoon in Santa Barbara on a day that highlights exactly why Santa Barbara is such a remarkable place. It's also good to be here in what I now understand is gallium nitride valley. I had not thought of it in that way before, but if you think about it, it kind of fits, and that's quite good. UC Santa Barbara has a very important role if you look across the country in terms of innovation around LEDs and lighting, around energy efficiency broadly, around solar. So I think this notion of a gallium nitride valley and sort of being present at the creation of that valley is quite a good thing. I also think this is a great group. The speakers this morning were very, very exciting. I was excited by Umesh's discussion about digital power electronics, because the number of people who get passionate about digital power electronics, I think, are 12 in the country. And yet it's one of those markets that's enormous, and yet we don't spend a lot of time on. And so I think that kind of innovation that's coming from folks across the room here is very, very exciting. Back in 2005, as energy prices started to rise, I started collaborating with the Mckinsey Global Institute, looking at this theme that we started talking about of energy productivity. How do we get more GDP out per unit of energy coming in? Because like capital productivity and labor productivity, our view was that countries and companies that use resources more wisely, over time, were going to be dramatically more profitable than those that didn't. And so that was the genesis of a whole series of McKinsey work, the McKinsey greenhouse gas abatement curve that many of you folks are familiar with. It said the United States had 1.1 gigatons, roughly 20% of U.S. CO2 emissions were associated with energy efficiency reductions. Were, if you will, the cheap part of CO2 abatement, and a really important part of focus there. For my sins and that work, Secretary Chu called me on, it was New Year's Eve of 2008 going into 2009 and said, I need you to come back to Washington. I said, no, I got a job. I really like my job. I don't want to go to Washington. And he said, no, I really need you to come back and to spend this $35.2 billion. Do it really quickly, do it really wisely, and don't screw it up, because what you're doing is you're making a down payment on the nation's energy and environmental future. Oh, by the way, you have to get it done in 18 months, because that's the amount of time Congress has given us to do that. Interestingly, UC Santa Barbara was a beneficiary, and several of the companies in this area were beneficiaries of that funding. All told, 5,000 award recipients across the country. And when you look at somebody like the OPX Dow deal that was KT mentioned earlier, you get very excited about a set of down payments beginning to translate into real and lasting impacts on the energy economy. So I spent 2 years in Washington, and at the end of September, I returned back to the West Coast where my family had stayed and returned to the private sector. And so now spend most of my time between big energy and big technology, and looking at the interface between those two. Big technology who says, boy, selling to big energy is a real pain. Big energy is not quite sure I want to adopt the new technologies that are coming down the pike at scale in the way that perhaps the market would suggest. What I thought I'd do this afternoon is make four basic points, and we'll try to do it in a way that is somewhat entertaining, otherwise everyone will retreat to the beach. The first is that sustained economic growth depends on significantly improving our energy and resource productivity broadly. There is a wonderful opportunity in the market today. It's called how do we build out China and India. We don't get to take advantage of that market unless we find dramatically more productive ways to make that possible. The second observation, particularly for this group, is that sometimes the most important innovations occur on the demand side of the equation, even though we spend a lot of our time thinking about the supply side of the equation, because the way that we use the power ends up creating the value in the marketplace, and therefore sometimes the innovations on the demand side end up having higher returns than the ones on the supply side, at least up front. And so I will talk a little bit about where the demand side innovations are taking place. The third is that energy innovation is happening a lot faster than the market expects. One of the privileges of being in Washington with Secretary Chu and the technologists at DOE was to see the flow of new ideas, and the rate of change in the underlying technologies are much faster than they have been in energy and resources for some period of time. We'll talk about why that occurs. The only problem is they're not happening quite as fast as the entrepreneurs would like. It took 60 years for coal to replace wood, and it took about another 50 years for oil to replace coal. I think we can do it in 20 or 30 years, but that's not 5 or 6 years, and so it's a very different kind of time horizon. And then the last point, and perhaps the one I'll dwell on the most, is that innovation in this space depends heavily on managerial leadership. We will talk a lot about really cool and sexy technologies, and yet the biggest missing element when I was in Washington and seeing all this technology come through were the managerial disciplines to take that technology and integrate it at scale into the system that we talk about as the energy system in the world today. That managerial discipline is the capability that I think companies and frankly countries need to develop in order to take advantage of the productivity that comes from these new technologies. So managerial leadership is critical. To put this in context, I thought maybe I'd tell a couple historical stories. Sunday afternoon in May of 1765, James Watt figured out what to do with that stupid Newcomb engine that he, as the instrument mechanic for University of Glasgow, was told to fix. He said, I don't want to fix it. It's a lousy, inefficient engine. It doesn't really work very well. And he figured out essentially how to improve the energy efficiency of the Newcomb engine by about 75%. That was the core value that Watt created in doing that. And what that allowed you to do was to use a coal-fired steam engine to replace water wheels in a core set of manufacturing processes. First, actually in coal mining, that was the key problem he was trying to solve, but then in a whole set of manufacturing enterprises. A demand-side innovation, how do we use the energy in a much wiser way, that opened up dramatically larger markets for a set of technologies. What Watt's innovation did was it accelerated the rate of real economic growth and productivity for almost a century. Huge innovation that drove productivity for almost a century. And what's important to realize is that at the moment that Watt is doing this, Thomas Malthus is sitting there writing and saying that England can never grow beyond 6 million people because we've reached the limits to growth. And I think this comes back to the point that was made right before lunch, which is that it is in these moments of constraint that innovation takes place. That's when real innovation occurs, and we are facing one of those moments of great constraint. With oil at $110 a barrel, with steel approaching $1,000 a ton, we face a period of constraints, and so what you hear are a group of folks on the one hand saying the end is nigh, and then a group of innovators saying, hey, I know a better way. We can actually innovate our way out of this. And what Watt demonstrated was this link between innovation and GDP growth and productivity, that innovation across the last 300 years has really been driven by, economic growth has really been driven by innovation. And that the folks in this room who drive that innovation engine are in fact the core to driving the economic growth engine. But it is important to realize that it wasn't until 1776 that Watt actually sold one. 1765 he invents it. He actually can't build the Watt steam engine until 1776, until the iron makers of the cannonade for the Revolutionary War in Britain could make the materials strong enough to handle the pressures in Watt's engine. So he needed the defense industry to come up and to grow it at enough scale to be able to make the Watt steam engine work. He and his partners took another 6 years to figure out how to apply it in a core manufacturing operation. So it wasn't until 1782 that they actually applied it in a textile mill, where we always think about what the steam engine did. By 1800, there were 80 of them in operation, but you didn't actually see it in the GDP statistics until 1832. So it took almost 60 years for the innovation to hit the economy. And then you saw the massive improvements that came from that. So dramatic innovations. Oh, by the way, Watt gave up 90% of the equity in his company in order to get it commercialized across that period of time. So and he died a rich man. He was a happy man. He changed the world. But it wasn't exactly all a lay down hand in 4 or 5 years that I think some folks want to have. A similar story is what Henry Bessemer did with the invention of modern steel making. Henry Bessemer wanted to figure out how to make a cannon that could shoot a 12-pound ball. And steel was the only material, but it was too expensive. And so, because it took a week and it took basically 3 tons of coal to make 1 ton of steel, so it was uneconomic and it was bad steel. And he figured out how do you blow a bunch of oxygen in there to get that whole process to happen much more rapidly, so I could use it for 20% of the energy in a day instead of a week. And that transformed the manufacture of steel, and it transformed the urban environment around the world. It allowed the United States to build up around large urban centers, because without steel of that strength and quality, you couldn't get there. But these are the kinds of innovations on the demand side. Huge innovation, 75% on the one hand, 80% in the case of steel, much less energy input per unit of output in order to transform the underlying markets in which we operate. So I came away from my time in Washington very, very excited about the change that is in fact underway. I would argue that we are seeing the beginning of that kind of productivity change again in the face of the constraints that we face here in the United States and we face around the world. A few technologies that get me super excited, but in each one of them what I'm going to talk about is it's not just the underlying chemistry, but it's the package, it's the system that in fact makes this work. So a year ago, advanced batteries cost $1,000 a kilowatt hour. New battery manufacturing facilities, we funded 29 battery manufacturing plants under the Recovery Act program, should be able to deliver for $350 a kilowatt hour by the end of next year. You can buy them for $450 today, $350 by the end of next year. And if you're driving a car and you can get a battery for $250 a kilowatt hour and 200 watt hours per kilogram, every car wants one. Why? Because it is a very cheap way of energy efficiency. It provides better acceleration and better safety than the alternative technology in the market. So again, to the point of side benefits being as important as the core energy benefit, a lot of folks will actually buy the batteries. If you look at the new Porsche coming out, hybrid Porsche coming out, for example, it's all in acceleration because people will pay for the acceleration. So the ancillary benefits are important. But all of a sudden, it isn't just about the battery. It isn't just about the battery chemistry, because that's about half of the value. The other half of the value is the dispatch software that makes up for the failings of the chemistry, that makes sure that the temperature stays at the right level, that does the right level of discharge at the right time. And then the other value is in how you integrate it into the platform. Because if you just stick a battery in the existing platform, you don't get the value that you do from out of the entire system. So it's redesigning the system that makes the value possible. So one of the very important keys to the innovation that we're seeing in energy technologies now is this ability to link software with chemistry. This is a difference to the innovations that we saw 50 years ago. We didn't have software that could make up for the advances. The software scales in ways that the chemistry might not. Another great one is LED lighting, a core capability at UC Santa Barbara and in the startup community around it. Lighting accounts for about 15% of U.S. electricity demand. And what LED lighting does is it brings Moore's law to bear in an energy environment. LEDs cost about $200 for a 100 lumen bulb today. Should be $8 to $10 for a 200 lumen bulb, probably by 2015, maybe a little bit earlier if you talk to some of the proponents. But again, the key is putting an LED light bulb with the appropriate software technology. All of a sudden, then what you have is a building becomes an integral part of the grid. Because what you can do with an LED light bulb, unlike either a fluorescent or an incandescent, is you can vary the intensity of it much more readily and actually have the power vary. If you vary it on an incandescent bulb, you just waste the energy as heat. If you do it in a fluorescent bulb, you lose a lot of color, but the LEDs have much greater range for being able to do that. And the net effect is you have now much greater ability to change the energy dynamics of a building than you ever could before. So every LED is going to come with a software and a wireless communication piece back to the central control system, and the local utility could say, can you just turn all the LEDs in the building down by 4%? And that ends up being a much cheaper way to meet a whole set of load constraints in a peak period than does turning up a big natural gas-fired power plant. And that kind of ability to combine these technologies into core systems, to take the price of the core technology down to a very, very low level so that the market wants to buy it as the primary product, but to integrate it into a system that does a set of things that the technology that it's replacing never could do, is the core of the innovation story that we have. Umesh talked about digital power electronics. This is an area that I find a great deal of, I'm one of the other 12 in the country who are passionate about this. The transformers that we use, the transformer you have outside your house, was invented in 1885 by Edison and Westinghouse. They invented the technology in the same summer. They had a great competition to see who's would end up winning. Westinghouse ended up winning the competition, so we have the alternating current system coming out of there. And we designed our U.S. electrical system for the next 125 years to deploy the technologies that Edison, Westinghouse, and Tesla invented in 1885 across the United States at scale. That was what we designed our utility system to do. Technology didn't change very much. It's basically the same core technology. Typical transformer costs $20,000. It weighs about 10,000 pounds. It takes up about 250 cubic feet in a substation. And the ability to bring either silicon or gallium nitride, silicon carbide, gallium nitride, great competition ahead. We'll decide whether this is the silicon carbide and gallium nitride valley or just the gallium nitride valley. But the ability to deliver the results with 1/10 the energy, so take all the waste out of the system, and 1/100th the size. Just think about a major urban environment where you don't have to have a substation that takes up a block of major urban real estate. I can do it in 1% of the footprint of size, and all of a sudden you invest in this as a utility just on the basis of the real estate freed up, no less the energy efficiency that comes from that. So these are innovations that benefit from highly scalable fundamentals. The availability of very low-cost sensors, the availability of software. We're riding on the innovations that are occurring in consumer electronics. The ability of the batteries are benefiting a lot from the consumer electronics revolution. So the core of it is we, as in the energy world, don't have to bear the full weight of innovation. What we have to do is adapt that innovation and bring it to bear in the networks that exist here. So what this does is it puts a focus on managerial leadership. How do managers then cope in this kind of environment? How do managers position their companies, and frankly, how do leaders position their countries to take advantage of changes that are at this scale and importance? So 10 principles to think about. The first is, are you spending enough time at the bleeding edge of technology? One of the things that's true in periods like this is that there are black swan events. If you bring in the market for batteries at $350 a kilowatt hour is about 500,000 units a year in the United States. At $250 a kilowatt hour, it's about 12 million units. So all of a sudden, it isn't a linear progression of one to the next. All of a sudden, you have a huge market that opens up when you hit the key price point. As you think about projects, are you planning around high energy and high resource costs? Are you planning for a $150 a barrel of oil world? Are you planning for $1,500 a ton of steel? Because the optionality that you design into a project, if you think that high prices might come, because the likelihood is there that they will, usually wins out over a long period of time in terms of investment decision making. Are parts of the portfolio really designed to deliver 80 or 90% improvements, the kind of improvements that Watt and Bessemer brought to bear? Doesn't mean that the entire portfolio is going to do that, but you have to have experiments going on that are shooting for that. Over the last 100 years, if you were a manager and you delivered 1 to 3% every year, you did really, really well. But in this period of time, you have to have parts of your portfolio of innovation that drive further and faster than that. And at the core of this, can you package these innovations into simple systems? I talked with the CEO of one of the big utilities in the United States, and he said the first time somebody took one of those smart grid gizmos and put it on my system, it made it worse. And the second time they did it, it made it even worse. And the third time, it was worse than that. And by the time we had 5 of those gizmos on there, it was really operating badly. Now, by the time we got 30 pieces of equipment on there that all worked together, and we had to go through about 180 to find the 30 that really worked, then we really had something, and it operated 25 to 30% better than the system had before. But we can't do it in a way that all of a sudden we just sort of throw things at the system. These are systems, these are networks. They only work as networks. And if we try to do it one piece at a time, incremental, it won't actually get us there. Another broad theme is this theme about instrumentation. Have you instrumented your company? Have you instrumented your institution in a way that allows you to capture the data that's necessary to take waste out of the system? Again, every light bulb with a sensor on it is the metaphor for what we're seeing across companies. And then the theme that we've talked about broadly, how do you create that tension in the organization? Because organizations innovate when they face constraints. They don't innovate when they have huge surpluses lying around. And so this notion of forcing companies to accelerate the rate of productivity, to hold your people accountable for moving the rate of productivity year by year becomes enormously important. So the core technologies that we have been talking about, that we use today, the core technologies that we use in energy, were mostly invented 125 years ago. So maybe we have an opportunity to take the next step. And in this room, I think you see the kinds of technologies that can take us to the next level. But it requires this kind of managerial leadership, this kind of managerial judgment to take those technologies and, as Umesh was talking about, put them into packages that make it simple for people to adopt and to use, into packages that deliver dramatically more benefits at the same or lower cost than the incumbent technologies. And that's the characteristic that occurs mostly on the demand side. The revolution of industrial revolutions tend to begin with demand-side innovations. And I think that's what we're beginning to see in the US market, in the global market today. And with that, why don't we stop, and we'll be happy to take your questions.